Let's look at a two-sided hypothesis test for proportion using a TI-Nspire. Here's the idea behind hypothesis testing. We have a hypothesis, which is a guess about what is true. We collect data to test the hypothesis. We plug the data into a formula and then use the result to determine whether or not our hypothesis is true. For example, I have a pair of 7-sided dice in my office. Are they fair dice? In other words, is every side equally likely? If the dice are fair dice, then the probability of a particular side coming up is 1/7. Here's the question. Is the probability of a 7, that is the probability of rolling a 7, is that really equal to 1/7? That's not a 7. That's not a 7. That's not a 7. Oh, there it is. I rolled a 7. So again, is the probability of a 7, the probability of rolling a 7, is that equal to 1/7? I was curious. I have a pair of 7-sided dice. I rolled the pair 50 times a day for 200 days. No joke. That is 10,000 rolls of the pair of dice. It's like rolling one die 20,000 times. The result? 2,755 sevens out of 20,000 rolls. Expressed as a decimal, that's 0.13775. Note that 1/7 is 0.142857. Is that far enough from 1/7 to conclude that the probability of a 7 is not equal to 1/7? Recall that the null hypothesis means no change, no difference, and we represent that with an H0. The alternative hypothesis is that there is a change, there is a difference, and we represent that with an H(a) or an H(1). So H0, the probability of rolling a 7 is equal to 1/7. H(a), the probability of rolling a 7 is different from 1/7. Represented symbolically, let P equal the probability of 7, that is the probability of rolling a 7. H0, P equals 1/7. H(a), P does not equal 1/7. Here's how we'd use a TI-Nspire. So you choose Calculate, and then press Enter, and choose Menu. Press the Menu button. You'll get a menu that looks like this. So you choose Statistics, and then Stat Tests, because we're running a statistical test. And we want a 1 proportion z-test, because we're just testing one proportion. We don't have two proportions that we're comparing with each other. It's just one proportion. You enter the data. P(0), that's the hypothesized proportion from the null hypothesis. That's 1/7. The number of successes is X, that's 2,755. Total number of trials is N, that's 20,000. The alternative hypothesis, H(a), is that the proportion does not equal P(0). And then we choose OK. When we do that, we get a p-value of 0.0390. What is the p-value? This is short for the probability value. It's the probability that we would get a result this extreme or even more extreme if the null hypothesis were true. So here, the p-value is 0.0390. If the p-value is less than 0.05, where does that come from? That's the default. If you're not told a level of significance, you just let the level of significance be 0.05, which corresponds to a 95% confidence level, because 1 minus 0.95 is 0.05. So if the p-value is less than 0.05, we reject the null hypothesis, because there is less than a 5% chance that we would obtain a result this extreme or even more extreme if the null hypothesis were true. As textbook author Mario Triola puts it, if the p is low, the null must go. So again, if the p-value is less than 0.05, we reject. P, probability of rolling a 7. Here's our null hypothesis. Here's our alternative hypothesis. Since the p-value, 0.0390, is less than 0.05, we reject the null hypothesis and conclude that the probability of rolling a 7 is not 1/7.